Okay, so in this video, we're going to be looking at what we call the kinetic model of matter. So we're going to look at how we describe the different states of matter and the experiments that showed us that they were actually like this. So first of all, let's look at what we call the distinguishing properties of solids, liquids, and gases. So the solid, you can see over here, maintains a fixed shape and volume. So even if we were to take it somewhere completely different, turn it upside down, whatever, it would keep the same shape and it would keep the same volume. Whereas a liquid is slightly different. So it will keep a fixed volume, but its shape can change to fit its container. So if we put it in a different container, it will take a different shape. Gases have neither of those things. So gases can change volume and their shape to fit whatever container they're in. So they can expand or contract as well as move around. Okay, so that's what we call the distinguishing properties of the three states of matter. Now what we look at is actually describing them in terms of the arrangement, motion and separation of the molecules. So on the left-hand side, you can see a solid. The solid, the atoms or molecules, depending on what it's made from, are in what we call a regular arrangement. So you can see that from the picture. And they're really tightly bonded in space, so they don't actually move very much, but they do vibrate. Whereas in liquids and gases, the atoms are arranged randomly, and that's because they're free to move past one another, so they're not fixed in a particular position. So that's the arrangement. Let's have a look at the motion separation as well. So atoms in solids have very small separation, so the diagram doesn't give a great idea of scale actually. So in solids, they have very small separation and very small speed. So they are moving, but not particularly fast. Whereas in gases, they have a large separation. So the diagram is showing that accurately. And they have a large speed as well. And those two things are actually tied together. Okay, so that's how we describe the different states. And liquids is somewhere in between those two. So now what we're going to look at is how a material actually changes when it's heated using this kinetic model of matter. So on the left-hand side, you can see a low temperature material, and on the right, you can see what happens as its temperature increases. So the average speed of the particles increases as your temperature increases, and that causes the spacing to increase, which is why a material expands. But the key thing to note between the two models is the atoms stay the same size. So a lot of people get this idea in their head that when you heat something, it expands. So they think atoms themselves must expand, but no, it's the actual spacing that expands. The atoms stay the same size. Okay. So let's actually dig into that a little bit more. What is the relationship between temperature and average kinetic energy? These are the two things which are fundamentally related. So if we measure temperature in Celsius, like you can see over here on the right-hand side, you can see we get a linear type relationship. So it is a straight line, but it does not go through the origin. However, if we measure it in a different temperature scale called the Kelvin scale, you can see it's a directly proportional graph, a straight line going through the origin. And we can actually develop an equation for this. So the average kinetic energy, so the reason it says average is because molecules have a range of kinetic energies. So if we have a bucket of water, all those water molecules will not have the same kinetic energy. They'll have a range, but at a certain temperature, they'll have a certain average kinetic energy. And as temperature increases, that average value increases as well. So you can see that the equation describes kinetic energy and temperature as directly proportional, as long as temperature is measured in Kelvin. And then there's these constants of proportionality, the 3/2, and then what we call the Boltzmann constant, which is like 1.38 times 10 to the minus 23. So the amount of kinetic energy is a really small number, but it is directly proportional to temperature in Kelvin. So I think a sensible question here is, how do you convert between Celsius and Kelvin? It's pretty straightforward. You just add 273. It's actually 273.15, I think. but this is how we convert between the two. It's fairly straightforward. Okay, so the key from all of this is temperature and kinetic energy are directly proportional as long as the temperature is measured in Kelvin, or linear if they're measured in Celsius. But the big idea is higher temperature means higher average kinetic energy. That's the big picture thing here. So we've seen that as we heat something, the separation distance increases. And you'll have noticed that as we go from solid to liquid to gas, separation increases. So what effect does that have on the intermolecular force between the atoms? Well, the electric force, which is the force that's responsible, gets weaker as the distance between charged particles increases. So if we heat something, we increase the kinetic energy, that gives you a bigger separation, that then gives you a smaller force between the molecules, which is why they can eventually break off and escape. If you want to know a little bit more, this is actually describing Coulomb's law of charge, which actually says distance and forces have an inverse square relationship. So if you double the distance, you will quarter the force. But that's an extra bit of detail in there. We don't need to know that. It's just how reality actually works. So how did we actually know about this, describing the states of matter like this, and know about atoms and things like that? Well, it's actually this experiment carried out by Robert Brown which tells us this, first with pollen grains and then latterly with smoke particles as well. So in either scenario, what you do is you introduce a bigger particle that is free to move. So it might be a smoke particle, it might be dust, it might be pollen, but there's a big particle that you can actually see, even if you might need a microscope to see it. So that's the key idea here. And then you watch what happens to that big particle. And what you notice is it moves in random motion. So what does random mean? It means it's impossible to predict what the particle will do and when it will do it. We have no way of predicting what's going to happen. So let's look at those two different. So let's first look at it with smoke particles. So that's what you can see here. These brown ones are the smoke particles, which are in random motion. And these blue ones are the atoms of the gas that they've been placed in, probably air. So what happens is these blue ones change the direction of the smoke particles when they collide with them. And that's what you saw on the previous diagram. So you will notice the smoke only has small changes in motion, and that's simply because the mass of the atoms is considerably less than the mass of the smoke particles, so they don't have a massive effect on it, but they can have a change in its motion because they're traveling at high speed. So that's with smoke, and you typically need a microscope to observe this one, so you need to look really closely to see this in action. With pollen, which is the first one that history tells us was done, this is all embedded in water. So what you can see around the pollen is all water, and these are your pollen grains. And you see exactly the same thing. The pollen grains change direction when the liquid molecules collide with them, and the pollen grains therefore move in random motion. So what we can see is that both liquids and gases give us this random motion, which is how we're able to describe their nature right back at the start of the video.